So this is about sets, okay? And I'm just gonna, today probably is gonna be mostly definitions as usual, okay? Because we're gonna set up the language that we use, okay? Then we're gonna use logic to define some ideas because we already know logic, so we can be more formal, okay? All right, so let me start with the definition. So what's a set? I'm recording, yes. So a set is just a collection of elements, okay? And this collection doesn't have to be ordered. So it's an unordered collection of elements. What elements? Whatever you want, okay? Anything. So a set is an unordered collection of elements. Okay, so for example, I don't know, let's say, typically we use capital letters to denote sets. Like for example, for propositions, we use lowercase letters, right? P, Q, R, S, T, etc. For sets, we usually use A, B, C, but capital letters, okay? For example, let's say the V is a set of vowels. Set of vowels in the English alphabet. So what is this set? For example, right here, when you describe a set, you can do it this way. You can just tell me in words what it is. As long as everybody understands what are the elements in that set, you're good to go. Now, there are ways to denote this. For example, this is the following. So there's something called, as you know, the roster notation, that basically what it does is the following. We draw a pair of curly braces. Whenever you see a pair of curly braces, this means a set is being given to you. And then inside, we just list the elements of that set. For example, what will be the elements in this set? So A, B, oops, A, E, I, O, U. Yes? The vowels of the English alphabet. So how many elements that this set has? 5 elements, okay? Now, the order is not important. Notice that I said unordered collection of elements. So, for example, this set will be the same, we're going to talk about equality soon, as this set. Okay? And here I also double the O on purpose, okay? What you care about a set is whether a given element is in there or not, okay? Here we're not talking about how many O's you have, how many A's you have, okay? So, do you have A in both sets? Yes. Do you have E in both sets? Yes, and so on. So, these two sets are exactly the same. The order doesn't have to be the same, and the amount of time that each element shows up in the set doesn't matter here. Okay? You have to think of this as having a bag, and all you care about is whether you have something in the bag or not. Okay? Do I have an O? Yes. Do I have an O? Yes. That's good. Okay? All right. So those sets are the same. All right. So as I mentioned, this is called the roster notation. Other sets that are commonly used in mathematics are, for example, the natural numbers. So the natural numbers, the notation, the letter that we use for that is a boldface N. And what is this set? But let's see, some people include 0 here, and other people don't include 0 here, because some people argue, okay, at the beginning, the natural numbers are supposed to be the first number that we use as humans. And they were the counting numbers, 1, 2, 3, 4, etc. 0 came much, much later. There was a time that if you believe in 0, you were a witch and that kind of stuff. Like 0 was a dark idea. Humanity has been interesting, okay? But, you know, nowadays, mostly we include 0 here. In fact, there's something called Peano's axiom of number theory, and the first axiom is 0 is a natural number. Like, let's end the discussion here. Let's say it's a natural number, and we move on with our life. Okay? So I will include it. So 0, 1, 2, 3, 4, you know, and so on. We're going to talk about these 3 dots soon. This means, yes? Yes. So this means, and so on. Okay? So in other words, once the pattern has been established, then you have the right to write this, because this is an example of an infinite set. You cannot just write all the elements here. We're not going to be done, right? There are infinitely many elements here. So you establish your pattern, and when you say and so on, that means anybody that walks in should be able to look at this and figure out what's the next and the next and the next. Okay? If I do this, then it's not clear what's the next one. Maybe I'm talking about binary only. and then it's just zeros and ones, right? So you have to establish your pattern, okay? All right, so that's the natural number. So these are examples of what we call the roster notation. You list the elements. Let me give you some symbols here. So boldface C. We typically like to do this kind of stuff with the plus. So this is the symbol for the integers. Okay, so the integers, and what are these? These are the natural numbers together with the negative version of them. So that will be 0, 1, 2, 3, 4, and so on. But also -1, -2, -3, and so on. Okay? So that's what the integers are. And then if I use this symbol, this means the positive integers. This little plus, the positive integers, and if you want to talk about the negative integers, typically we put a little minus here on top. Okay? So who can tell me what will be the elements here? 1, 2, 3, 4, and so on. Okay? Now this is the roster notation, and it's nice because in this case, notice that these sets, even though they are infinite, we can list the elements. Later on, when we talk about cardinality, it's going to be very important. Okay? The point is that there are different types of infinity. All right? We are only going to barely scratch the surface on this idea. But anyways, this is the nicest type of infinity, if you will, that you can list the elements. Okay? But for example, sometimes there are sets that are not that easy to list the elements. Listing means that there is a natural order. Like, you can tell this is the first guy, this is the second guy, this is the third guy, and so on. Okay? Now, how about the rationals? The rational numbers. How do we define this? So how do we write it? So you will learn later that you can list the rationals. That's actually in a very strange way. Okay? It's not that straightforward to find a listing of the rationals. Because remember, these are all possible fractions that are out there. Okay? But then how do we define this? Well, there's another way to define sets. The above is the roster notation. What I'm about to write is what we call the set builder notation. Basically, you're going to describe here how the elements in your set look like. So describe how the elements look like. Then we draw a line like this, or sometimes two dots. Okay, that stands for such that. And then over here, we put the condition that the element has to satisfy. So condition to be in the set. Okay, it's called the set-builder notation. So for example, for the rationals, how do elements here look like? They are fractions. So they have the form P over Q, such that what condition must be satisfied? Q cannot be 0, and what else? So what are P and Q? They have to be integers, right? So these are elements of the form P over Q, where P and Q are integers, and Q is different than 0. This is called the set builder notation. And for example, this is very handy when you are dealing with a very large set and there's no straightforward way to list the elements. Sometimes it cannot be listed, but then you do have a way to describe what does it mean to be an element in that set. Okay? So that's when this comes very handy. So you describe how the elements look like, and then you say what condition must they satisfy to be able to be elements in your set. So rationals are fractions, but not whatever fraction. For example, pi over e is not necessarily in the rationals. Yes? Why? Because pi and the number e, they are not integers. Okay? So these are fractions where top and bottom are integers, and the bottom cannot be 0. All right, questions about this? Another example is, for example, intervals are also sets. For example, the interval 1, 2. What is this? This will be the set of all numbers x, such that x is a real number. And what else?
Between 1 and 2.
and x is between 1 and 2, right? So it's bigger than 1 and less than 2, not including because I'm using parentheses. Yes? So in the same way, right? So similarly, as you know, you can then define, I'm going to leave this as a homework for you to define it formally. You have, a comma b, then a comma b, for these 4 versions of the intervals, what changes is the inequality that you use here, right? Which one you include, which one you don't include, and so on. And as you know, brackets means included, parentheses means don't include. Okay? So this is all notations that we have to talk about intervals. Okay, questions? Do you understand this? All right, perfect. So let me give you an example. So for example, let A be the set 1, 2, the one that we have above. Find an element. So who can tell me what's an element inside this set? 1.5. So for example, 3/2, right? How do we write this down? So we can say 1.5 is an element of A. Now, instead of writing this in words every single time, because you're going to be doing this a lot, then we have a special symbol for this part right here. It's an element of. This we denote it by this symbol. Okay? So it looks like an E, but we curve it to a C with a line in the middle. Okay? So we write the 1.5 is an element of A. Okay? So you read this as 1.5 is an element of A. Give me an example of something that's not an element of A. 0. Okay? So 0 is not an element of A. Again, we're defining the grammar here. We're going to be using these symbols a lot. So if you have trouble with symbols, this is the time to understand this. Okay? So once again, we have a way to say this. So how do we in mathematics say, whenever we have a notion, how do we say the opposite of that notion? What do we typically do? We just crush it, right? When you have the equality, how do we write different? The equal sign and we crush it, right? So an element of, this is the symbol, okay, now an element of is this symbol, scratch out. So the way we write this is like that, okay? So we write 0 is not an element of A. So when you see that, the way you read it is 0 is not an element of A. Are you okay with this? All right. So now that we understand this, then let me define a special set, so definition. This is actually one of the axioms of set theory. There is a set that has no elements. Okay? And we call this the empty set. Okay? So there is a set with no elements. This is called the empty set. Okay, so we write different ways to write it, but the most commonly used way is this symbol, which is the one that I'm going to be using. Okay, so this is not a vertical line. Okay, so it's like a little diagonal. If you do a vertical line, then that's capital letter P in Greek. That's the letter phi. Okay, so that's why if you do a vertical line, I know what you mean, but technically it's like that. But also sometimes you will see some books write it as a pair of curly braces without anything inside. Okay, just to say that look, this is the set that has nothing in it. Okay, so understand that this is the empty set and it's the set that has no elements. Any other set is going to have elements inside. Is that clear? Yes? Okay, so let me ask you a question then. I guess question / example. So is this equal to this. So, and justify, of course. So every time that I ask you a question, your answer is not just a yes or no. It has to be followed by some reason behind. Okay. So let's see. What do you think? We haven't talked about equality, but what I'm going to define it soon. But what do you think equality between two sets means? What does it mean for two sets to be equal? What do you think? If they have the same elements. Remember, a set is a collection of elements. So two sets are the same if they have the same elements. Okay. We're going to formally define it now. So this is a set. So you have curly braces, right? This is a set. We just define it. Are these sets equal? Why not?
This one has an element that is not this element.
Very good. This is not the empty set. This is the set with one element. What element? The empty set. Remember, a set is just a collection of elements. These elements, they can be whatever you want. In particular, they could be sets themselves. So you can have a collection of sets. In particular, this is a set whose element is the empty set. So if you think of a set as a bag, what's happening here is that you have a bag with an empty bag inside. A bag with another bag. And this is just an empty bag. They are not the same. Do you understand what I'm saying? So the answer is no, they are not the same. And the reason is because the empty set is actually an element here. So this set is not empty. Okay? Because the empty set is an element in here. Do you understand this? Okay, good. So now that we're talking about this, let me define equality. So two sets are equal if they have the same elements. I'm going to write this down formally. So definition, let A and B be two sets. Then A is equal to B if and only if A and B have the same elements. So formally, what I just said here is this: A is equal to B if and only if for all x, x is in A, if and only if x is in B. If this statement is true. Okay? In other words, A is equal to B means that this statement must be true. In other words, for every element in our discussion, it is in A if and only if it is in B. Remember, this means if x is in A, then x is in B, and if x is in B, then x is in A, right? That's how you break by conditions. It's a pair of implications. So as a formal definition, to say that two sets are equal is to say that this quantified proposition is true. Okay? That's what it means to say that two sets are equal. Any questions? So notice that this is also equivalent to say that if x is not in A, then x cannot be in B, and the other way around. If x is not in B, then it cannot be in A. Okay? Because remember, false and false is also true. So when you have false by conditional false, that's also true. All right. So let's do some examples. Let's see. I probably need to give you a couple more definitions before I need to give you the definition of subset before we can do another interesting example. All right, so that's equality. So let me give you another definition. Venn diagrams. So that's equality of sets. Number two, Venn diagrams. You have seen these already, most likely. But whenever we talk about a set, then there is a Venn diagram that we can always draw corresponding to this set. So what is this? So every time that we talk about a set, remember, a set is a collection of elements. So the natural question is, okay, what elements are you talking about? Okay. Oh, any elements. Yeah, but are you talking about cats, or are you talking about numbers? Or are you talking about cars, or person? What is it? So to make the discussion more clear, we typically establish a universe of discussion. That's a universal set, meaning I will tell you, for example, our universe is going to be the set of all numbers. So that means whatever I'm talking about is just about numbers. Cats and dogs have nothing to do with what we're saying. Okay? So the set U, we call it the universal set, or in short, just the universe. And this is just, the collection of elements that we're allowed to use. So this just means this is the collection of elements that we are allowed to use to make our sets. Remember, a set is a collection of elements. So where do you take these elements from? Well, from whatever is the universe that we establish. I'm going to show you why it is important to know what the universe is. For example, in all your classes, starting from college algebra all the way up to calculus, it's understood that the universe is the set of real numbers. So whenever you talk about a number, they are really talking about real numbers, unless they want to specify complex numbers are allowed. And then when you're solving quadratics, they tell you, also find complex solutions and so on. But if nothing's being taught, it's assumed that our universe is the real numbers. Okay? So unless a disclaimer like that is made, you should always be specify what the universe is, unless it's super clear. Okay, so given a set A, for example, I'm going to do it with an example, 1, 2, 3. The Venn diagram of a set is the following. So we draw a box, and now this box represents the universe. In other words, every element on our discussion is going to be inside this box, okay? So let's say that, and then what you do is a circle inside the box, and you put the letter representing your sets, and then, we typically, if there are a few elements, we just put them in there as 3 dots, or the labels 1, 2, 3, or ABC, whatever the elements are, okay? Now, of course, this is important because now you will see there will be exercises in which you're going to have different sets together. And then they all are inside the same universe, so you're going to have them all inside this box. And you have to show how they relate to each other and so on. And you will use that to answer survey questions. Okay? So this is happening in the homework later on. So something like this is what we call a Venn diagram. So the elements of A, they are written inside of A. Elements that are not in A, they are written outside of A. Okay? So I'll just put 1, 2, 3, like that. Okay? So for example, let's say that I'm gonna call this one, okay, 1, 2, 3, and let me put here 7. The dot with a 7. So by looking at this picture, for example, you can say that 2 is in A. Let's say that you don't have that description above, but you only see this picture. It's clear that 2 is in A, and you can also say that 7 is not in A. Because the elements that are outside of A, you have to put them inside your universe, but not inside the set A. Do you understand this? Later, we're going to see that this region here represents what we call the complement of the set. The complement of a set are the elements that are not in the set. Elements in the universe that are not in the set. So what's outside of A? Okay? So we say that 7 is an element of the complement of A. We get to that soon. Complement would be the equivalent of negation in logic. Most of the operations that you're going to see in sets, they have an analog in logic. Okay? The complement is like the negation operation. All right, so as a quick example, let's say that our universe is the integers, okay? And then the question is, what is this set? Who can tell me? Will this universe now specify? So above, when we wrote it, it was understood that the universe was the real number. You see, that's why I wrote here, x is a real number. This is all x's, but all x's such that what? Well, it has to be a real number and between 1 and 2. But now if I'm telling you that our universe is the integers, what can you say about this set? What is this? In other words, what is this equal to? Describe this set to me.
It's an integer such that x is between 1 and 2.
Okay.
And then all others are complements of the set.
But then what is this set? Is it an integer between 1 and 2?
No.
So what is this set? Is there an element in this set?
set itself.
There's no element here. This is the empty set. I'm telling you that we are only allowed to work with the integers. That's what I'm telling you by fixing the universe to be the integer. Yes? Now, if I write this down, this means numbers between 1 and 2. But do we have an integer between 1 and 2? No. So this has no element. So this is another way of writing the empty set, for example. Do you understand this? So you have to be very careful. It's very important to know what the universe is. If the universe is the real numbers, okay. There are infinitely many guys in here. Anything between 1 and 2. Yes? But now if I change the universe and say the integers, this is empty. Do you understand what I'm saying?
It's almost like saying undefined. No, no.
It's defined, it's just that it has nothing. Right? It has nothing in it. Are you okay with this? All right. So now that we have this notion clear, we're going to come back to Venn diagrams later on. Here I'm just defining these ideas because we're going to be using all of these little tools and words as we go along. Okay. Another common notion that we use whenever we have two sets, like when you have two numbers, you like to compare the numbers, right? And we have two sets, we want to compare them in a sense. Here, comparing really means the notion of containment. Is this set inside this other set? We have a fancy word for that. It's called subset. Okay? Given two sets, you could ask whether one set is a subset of the other one. Subset means that every element in this set is inside this other set. So this guy is bigger than this one, or maybe the same, but it contains this, like the name suggests. Okay? So let me define this. So definition. Let A and B be two sets. So we know what equality is. Now we're going to define subsets. So let A, be two sets. Then A is a subset of B. Denoted. So the symbol that we use for subset is this. Okay. So we put the two sets and then we use this little symbol. It looks like C. Okay. It's not like a less. It looks like a less than or equal to, but it's not less than or equal to. This is a curving. This is like a C with a little line. So A is a subset of B if every element in A is an element of B. Do you understand this? So formally, how do we write this? Formally, so A is a subset of B if and only if for all x, if x is in A, then x is in B. Okay? So when you want, and the reason why I'm giving you the formality is because this actually tells you how to prove whether one set is a subset of another one. If you want to prove that one set is a subset of another one, what you need to ultimately do is argue that this is a true statement. And how do you argue that this is a true statement? You need to show that for every x, this implication is true, right? How do you prove an implication? Let's see, we just did a test. We just did an exam on this. How do we prove an implication? How do we prove an implication? How? What's a direct approach?
Suppose it's true.
What's true? Assume, don't tell me that only one day has passed. You forget this already. You assume P, and then you prove Q. Yes? So when you want to argue that a set is subset of another one, what do you need to do? Start with an element in A, so let X be an element in A, and then you need to argue somehow that that element is also in B. So assume P, prove Q. This is your P, this is your Q. Do you understand this? Okay. Like I said, the basic ideas from before, they will carry over. Okay. All right. So to show that a set is a subset of another one, this is what you need to argue. Okay. All right. And then similarly, what do you think it means for a set to not be a subset of the other set? So A is not a subset of B, written as, a subset symbol, scratch it. A is not a subset of B, written like this, if what? What must happen?
There is some element in A that
Very good. So let's see. Let's practice our logic. Okay. So let's practice our logic. Let's say that let's say that you don't remember what it means to not be a subset. Hopefully you remember what it means to be a subset. Okay. That not a subset should be the negation of this, right? Not a subset. So you negate this. Let's negate this statement. And this way we practice that. So A not a subset of B is equivalent to the negation of this. The way we reinforce what we have learned. Okay, let's negate this. There was an exercise in the exam that you needed to negate something like this. Let's do it. So what's the negation of this?
some X.
That X is X, and then we need to negate the parentheses. Now, to skip a step to save time, we need to break this implication. So how do we write this implication? What's an equivalent way of writing?
X is not.
The negation of X is in A or X is in B. Yes? But now, as you know, the negation of X is in A would be, this means X is not in A. Okay? So from now on, instead of this, I will write X is not in A. You okay with this? So typically, this is what we mean by X is not in A. So now what is this? That X is an X, such that, so the negation of X is not in A or X is in B. Now let's negate using De Morgan's law. So what is this?
X in A.
X is in A and X is not in B, right? That's De Morgan's law. So what does it mean for a set to not be a subset of another one? It means that there is an element that is in an element of A, but it's not an element of B. So A has something that B doesn't. So A is not inside of B. Do you understand this? So if you want to argue that a set is not a subset of another one, all you have to do is find, you need to give me an example, right? It's an existential statement. Find an element that's in A, but not in B. That's all you need to do to show that A is not a subset of B. Okay? So A is not a subset of B means that there exists an X such that X is in A and X is not in B. Means that this is true. I.e., there is an element in A. I'm gonna write it in words what that sentence says. There is an element in A that is not in B. That's what we're saying. That is not in B. That's what we're saying in this line. Okay? There exists an element in A that is not in B. Are you okay with this? Again, these things, what you're seeing here is we're defining these ideas, but I'm also telling you how you need to go about when you need to argue these things. If I ask you to verify or to show that a set is or is not a subset of something else, you need to know what you need to look for. Okay? That's what this is doing for you. Okay, and then there is the notion also of proper subsets. So notice that the similarity, this right here, I'm never telling you that A and B cannot be equal. They could be equal because if A is equal to B, in particular, every element in A is an element in B. Yes? So this also allows the possibility of equality. It's like the less than or equal to symbol. Okay? Now, as you know, we have the less than symbol that does not allow the possibility for equality. Do you understand what I'm saying for numbers? Well, we similarly have it for sets. We just remove this, like we do for numbers. That's called a proper subset. Okay? So when you don't have the little line, it's called a proper subset, and it means what? Let's see, who can tell me what would that mean? If I say A is a proper subset of B, yes.
The two sets are not the same. Like they can have similar numbers, but they cannot be the same set.
Okay. For example, the set 1, 2, and the set 3, 4. Is 1, 2 a proper subset of 3, 4? So you have to be careful. What you just said, those two sets satisfy what you said. They don't have the same elements.
And I said that they can have similar, like.
What do you mean by similar? You have to be precise.
They can have, for example, one can be 1, 2, 3, 4, the other one can be 1, 2, and 3, but they cannot be the same set. They cannot have the same exact.
So now we have language to say that. How do we say that? A has to be a subset of B, and we need to throw in an extra condition. What extra condition do we need to throw in?
A cannot be.
A cannot be equal to B, right? So proper subset means A is a subset, so everything in A is in B. But now let's remove the fact that they could be. Do you understand this? So proper subset means this and A is not equal to B. In other words, there exists an element in B that's not in A. So B is larger. That's basically what we want to say. Do you understand this? Okay, so let me write it down. So we have subset, we have not a subset defined right here. Now proper subset. So A is a proper subset of B, denoted like this. So we just don't write the little line, okay? If A is a subset, so it has to be a subset of B. We know what that means. Every element A is in B. And now we throw in the extra condition. What's the extra condition?
A is not equal to B.
And A is not equal to B. Which then means that there has to be something. When two sets are equal, that means that there is one set that has something that the other one doesn't, right? Now here we're saying that everything A is in B. So what this really means is that there is something in B that's not in A, right? Because if you look at this alone, it could be that there's something in A that's not in B, but that's removed because of this part right here. Yes? So the reason why we're saying this is really because there is an element in B. You could replace that by the following sentence. There is an element in B that is not in A. In other words, B is larger, whatever that means. Okay, we're gonna formalize the things later, but whatever that means, B is larger. It has A inside, but it has more stuff. Do you understand this? That's what we're saying when we use the word proper subset. So again, why am I making a big deal out of this? Because if you need to argue that a set is a proper subset of another one, this is what you need to prove. So formally, A is a proper subset of B means that for all x, if x is in A, let me actually do it in two ways. So it means that A is a subset of B and A is not equal to B. Now let's translate this in parts. So A subset of B means that for all x, x is in A implies x is in B. And then and A different than B means that they don't have the same element. But since everything in A is in B, then what must happen here is that there exists an element in B. There exists an element in B. There exists x in B such that x is not in A. Okay? In other words, to show proper subset, you need to argue these two things. That this part here stands for A is a subset of B, and this part here stands for the fact that B has something that A does. Okay? So you need to argue those two. Subset, and then prove that B is larger. Okay? You need to argue those two steps. Sometimes it's just a word, it's just a sentence, and sometimes you need some work to do each of these steps. Okay? It depends on the problem. Right? Questions about these ideas? All right, so let's see, 3 minutes. So let me probably, okay, let's do an example, and then I'm gonna leave the proof, our first theorem, for later. So example, I just want you to tell me true or false. I thought the first question in the exam was gonna be easy, and I saw many of you writing the wrong thing. Like the very first question was what? 1 plus 2 equals, I don't know, I think 1 plus 2 equals 5 if and only if monkeys can fly. Many of you were telling me false. It is an if and only statement. So that's false here because 1 plus 2 is not 5, and false here because monkeys cannot fly. So what's false if and only if false? It's true. So a very simple true and false question, many of you were getting that wrong. Right? You just have to evaluate. So let's see, I'm going to give you some problems now, and you're going to tell me true or false, okay? let's practice this true and false business. All right, but of course in this context. So just tell me true or false. Let's see. And this is, of course, just to see if you understand the symbols, the meaning of the symbols. Some of these could be a little bit complicated. Like after we do the theorem, then of course it's straightforward, but some of these will require some discussion. The discussion we're gonna have it verbally is gonna get recorded, so you can always listen to the recording every single time. If I need to write something, I may, but you can probably just talk it out. Okay, so here we have 7 statements. The job is to tell me whether they're true or false. Okay, let's go one by one. The first one. Listen, do you want to think about those first? It's already 50, so I think there's not much time. So let's see. Let's do it together. The first one. What do you think? Is it true or false?
False.
Why? Remember, anytime you tell me something from now on, it has to follow with needs to follow with a justification. Why is it false?
Zero is an element.
Say that again.
Zero is an element.
What about it?
There's no elements in.
Exactly. The empty set has no element, right? And here we're saying 0 is an element of the empty set. That makes no sense. Yes? False. Number 2.
False.
Why?
Same reason as before.
There's
No, not the same reason.
They're saying that the set contains 0, which is a.
That's not what they're saying.
There's no bug in the bag.
This is saying that the empty set is an element of this set. That's what this is saying. Yes or no? Remember, here we're practicing the grammar. You need to know how to read this. This is saying the empty set is an element of this set. Is that true or false?
False.
Why is it false?
There is no set in that set.
Because the element here is 0. It's not the empty set. I mean, this is roster notation. This is a set that has one element. What element? 0. Not the empty set. If you want the guy to be here, you have to see it in there, written in there. But we don't see it, so this is false. The set has one element, 0, not the empty set. Yes? How about this one? So let's see, who can tell me in English? What English sentence is being said in here?
0 is a proper subset of an empty set, or the first set is a proper subset of an empty set.
How do you call this set? The set containing 0, not 0. 0 is a number. You will see later there's a difference. One thing is an element, another thing is a set. Okay? So the set containing 0 is a proper subset of the empty set. That's what this is saying. What do you think? Is this true or false?
False.
Why?
There are no sets in the proper set.
Why?
Because the empty set is not a subset.
You can have a set inside the empty set.
Why? What's the problem?
Yeah, empty set.
So I mean, you are all right. You need to know how to organize your thoughts. By contradiction. Suppose this is true. What would this imply if this were to be true? What would this imply? Proper subset in particular means that this will be a subset of this, by the definition. Yes? In other words, every element here has to be an element here. Yes? So 0, which is an element, will be an element here. So if you assume that this is true, it will lead to the fact that 0 is an element of the empty set. And what happens there? That's a contradiction. It doesn't make sense. Do you understand this? So this cannot be true, it must be false. Did you understand that reason? Yes? Okay, about 4. That's true. Again, why is it false? Let's see. If you're going to tell me that something is not a proper subset, how do you argue? What do you need to do to argue? That's the definition. To argue that something is not a proper subset, what do you need to argue?
It needs to not satisfy
that condition, right? So what does that mean? It's either, the negation of this. What's the negation of this? not a subset, the Morgan's law, not a subset, or equal. Yes? But let's see. They're certainly not equal, right? So if you say it's false, then they're certainly not equal, so the equal part doesn't work. So then you will need to show, you will need to argue that this is not a subset of this, right? That this is not a subset of this. But then what does it mean to not be a subset? Let's go back here. What does it mean to not be a subset? It means to say that there is an element in A that's not in B, right? So if you're telling me that this is not a proper subset, in particular, you're saying that this is not a subset of this, therefore, you're telling me that there is an element here that is not in here. But that's a problem. There's no element here. In other words, this is true vacuously because you cannot prove otherwise. You cannot prove me that this is false, because to show that this is false, you need to find an element here that's not there. But there's nothing to find. Do you understand the subtleties in here? That's why I'm taking time here, and excuse me, we are a little bit over, but it's important. I want you to think about this, okay? I want you to think about these little things. So this is true. And the reason is because you cannot prove otherwise. There's a theorem that actually says the empty set is a subset of any set. Because of this reason. Because otherwise, then you need to exhibit an element in the empty set that's not in the other set. And that's impossible to do. Also, think about the formal definition. If you say that the empty set is a subset of any set A, that's saying that for all x in the empty set implies x is in A. Yes, that's the definition. What is this? True or false? This is false. What happens when you have an implication and the beginning is false? It's automatically true. You can say whatever you want at the end, it's automatically true. So this will always work. So this vacuously satisfied. I know it's weird, but logic sometimes is weird. Okay, so keep that in mind. All right, how about number 5? False. Why?
Because the set of zeros inside the set.
Because it's not an element, right? Notice the symbol. We're saying, is that set an element in the other set? No. To be true, you will have to see this. You will have to be something like this. Maybe like this. You see, it will have to look like that. Like you have to see it in there, the whole thing. Okay? All right. How about 6?
Oh, sorry, false.
Why?
They're equal.
They're equal.
Because they are equal, and this says proper subset, right? I mean, it's a subset, but they are equal, so it's false. How about 7? Now this one is true, because they are equal, but equality in particular allows you to be a subset, right? Subset is a more general idea. Do you understand this? So reflect on these notions. We're gonna continue. You're gonna watch your videos on Friday. Start doing the problems to make sure that you get these ideas clear. So the other stuff that's coming hopefully will be more accessible. Okay.